All right.
Then you know.
All right, everybody. Welcome to the seminar this afternoon. We're going to have 3 talks. First by Vanessa here, and later by Bjørn Stiner and Bertram. But the first speaker today is going to be Vanessa Styles from Sussex, University of Sussex. And University of Nottingham, I didn't know that.
No, so John.
Oh, that's the other one. Oh, sorry. Oh, yeah, sorry. Yeah. Numerical approximations of a tractable mathematical model for tissue growth. Please, Vanessa.
Lovely, thank you very much for the opportunity to talk here. So this is joint work, as we see, with Joe Isles, who was a PhD student of mine, and John King, who's actually in the other program here at the Institute. And it's about numerical approximations of the most simple, pretty much, mathematical model that you can get for tumour growth. And so from the point of view of the model, then what we're thinking about is an evolving domain omega t, evolving in Rd, so D here is either 2 or 3, and this is going to represent the tumour, and the boundary of omega is going to be denoted by gamma, and the outward unit normal to gamma we're going to denote by mu. So the evolution of the boundary of this tumour is via forced mean curvature flow. So we've got capital V here is the normal velocity of the boundary, and so it evolves with beta. Beta here is just a positive parameter multiplied by kappa, which is the curvature of gamma, and then we have this forcing plus u divided by alpha, so alpha again is just a positive constant, and u here is the solution of a PDE which holds in the interior of gamma. So in our bulk domain omega t, we have the Platon of u is equal to 1, coupled with the Robin boundary conditions that grad u dot nu plus u over alpha is equal to q, so q here is another positive parameter in the model. So this is what we're considering, this coupled system of a surface evolving with this forced mean curvature flow, where the forcing comes from the solution of this PDE in the interior of the domain. And as the title suggests, the application associated with this is tissue growth, so just thinking of tumour growth. So what we're going to do is consider the free boundary problem that I've just told you about, and it is arguably one of the simplest macroscale spatially structural models for tissue growth that you can get. And so particularly we're not seeking biological realism here. What we want to do is we want to, because there are many models for tumour growth which involve lots of them, very complex, involve a lot of parameters, and what we wanted to do was strip down this model as much as possible so that we're, as we see in this instance, we've just got these 3 parameters, alpha, beta and q, and we want to see how changing those is going to affect the morphology of the solutions. And so even though we've got this very simplistic model, the numerical simulations that I'm going to show at the end show that this model does exhibit the growth morphologies that these much more complicated models have, and hopefully we'll be able to draw some conclusions about what the specific 3 parameters, how they affect the morphologies of these tumours. So we think of this tumour comprising of nutrient deprived necrotic core. So in the centre we have this, maybe the batteries are totally on. So in the centre we have this necrotic core where all the cells are dead and nothing's happening, whereas on the exterior to the tumour, so there's all the environmental tissues and things where nutrients supply nutritional value to the tissue, which is just in this thin rim around the boundary, and that's the nutrient-rich thin rim where you have the live dividing cells. So from the point of view of what's happening inside the necrotic core region, well, we model this by, so v we take to be the velocity of the the tissue in the tumour. And so tissue is degrading within this dead region, so we're taking the degradation rate to be lambda, so we just have quite simply the divergence of V is equal to minus lambda inside the necrotic core, and then we adopt Darcy's law for the velocity, so V is equal to minus K, so K here is just the permeability, and grad U, where U is the internal pressure of the tissue. So V here is the velocity of the tissue, and U is its pressure. And obviously, if we combine these two things and non-dimensionalize, then we get the Laplacian of U equals 1 that we saw, which is going to hold in our bulk domain omega t. And so where do the boundary conditions come from? So the Robin boundary conditions that we saw, they come from applying this thin rim limit. So what we're thinking about is we've got this thin nutrient-rich region surrounding the exterior of the tumour, and if we think of the limit of this tending to 0 to get us this free boundary problem of just the thin rim collapsing onto the boundary of the tumour, then formal asymptotics give us the rim collapses onto the interface and generates these two moving boundary conditions. So the first one, so if we recall from earlier slides, capital V is the normal velocity of the boundary of gamma, whereas V was the velocity of the interior, of the tissue in the interior, and so in general you would think that these two things should be equal to each other. Capital V should be little v dotted with nu, but because of the nutrient-rich the nutrients in the thin rim, then this capital Q is what's modelling the nutrient density on the surface, on the tumour surface. So we, in this particular model, take it to be constant. It can be spatially varying in more complicated models. I mean, we could add this in here, but for the moment we just want to take it as simple as possible. So we've got this one velocity law V equals V dot nu plus Q on gamma t, and then the second law associated with the normal velocity of gamma is this kinetic undercooling type mathematical law. So when the external pressure outside of the tumour is uniform, then the internal one, so remember U is denotes the pressure, is subjected to this regularization. So we have that U is equal to alpha times V on gamma t, and if we combine these two things and recall that we've got V is equal to minus grad U, then we indeed get this Robin boundary condition. So this is where the model comes from. And so lastly, we have where does the false mean curvature come from? So if we see on the previous slide here, so under 2 we have that U is equal to alpha V on gamma. If we regularize this with beta kappa term, so here we can think of beta as being the cell adhesion parameter, and so to do with the surface tension, then we have this false mean curvature flow, and that's where this is where the model comes from. And if you think about like the morphology of this tumour growth and how these how we're going to see the patterns that you naturally see occurring in tumour growth, so these sort of instabilities that occur, it comes from the fact that if we look at this model, the right-hand side of our Laplacian of U equals 1 equation, this is a volumetric sink that, as we've established, this reflects the loss of the necrotic material, and it destabilizes our free boundary gamma t. But coupled to that in this problem is the Q on the right-hand side of the Robin boundary conditions. So this is a surface source, so we've got a surface source, the competition between surface source and volumetric sink, which bring around these instabilities and give us the sort of standard tumour growth that we're going to see. And alpha and beta are our regularizing parameters. So what we want to do is numerically approximate this coupled system, and although it's pretty much the most simplest form of a tumour growth model, it's still, from a mathematical point of view, it's not trivial to analyse, for example, and numerically approximate. So I'm just going to restrict myself to 2 space dimensions for the moment. So we've just got this curve, gamma t, evolving in R2 in the plane, and So to numerically approximate this, so it's now curve shortening, forced curve shortening flow that we're looking at in two space dimensions, we use the following parameterization. So we parameterize our boundary by this parameter x, and we take I just to be the periodic unit interval. So we're always thinking about closed curves. We've got this closed curve, gamma of t. We parameterize it by x. And if we look at the terms coming into this, so we want to approximate v, which is a velocity, normal velocity. So if I were to multiply this equation, v equals beta kappa plus u over alpha, by the outer normal mu, then I've got v mu, which is nothing other than effectively, it's that xt term on the left-hand side of my integral. Then I'm integrating over my gamma t, which is why I get this x rho term coming in, and I'm integrating over my periodic unit interval I. So the weighting factor of x rho and the coupled to the integral over I gives me effectively my integral over the along the boundary. So my xt is effectively my v multiplied by the normal. If for the moment we just set omega equal to 1, so the next term is going to disappear, and then we have this beta x rho dotted with test function, the derivative of the test function with respect to our parameter rho. This is just the curvature term, beta times curvature. Curvature is the second derivative with respect to arc length. And then we've got on the right hand side, we've got our u times nu divided by alpha, again multiplied by this x rho squared and integrated over I to give us the integral of u divided by alpha multiplied by nu over our boundary. So this is our parametric formulation of this curve shortening flow. And so where does it come from? So it's introduced by Charlie Elliott and Hans Fritz, 2016. In fact, that was when the preprint came out. The actual paper came in real form in 2017. So what it does is it uses the de Turk trick to bring about special solutions to harmonic map heat flow to represent the equations in this form. And so what we see is this artificial tangential component in the velocity. So this is the term I told you to ignore. If we set omega equal to 1, then that term disappears, but the first term, the omega times xt, this deals with the normal motion in the normal direction, normal to gamma, whereas this second term, the 1 minus omega xt dotted with the normal, this is this artificial component in the velocity brought about by the de Turk trick with this 1 over omega corresponding to the diffusion coefficient in the harmonic map heat flow. And the nice thing from a numerical point of view about this parameterization is that it's very good. So this additional artificial component in the velocity is very good for distributing the nodes of your finite element approximation along the curve. So you don't get nasty clusterings occurring if your curve moves in a specific direction. And from the point of view of finite element analysis, prior to this, there was when with omega equal to 1, so there's no tangential motion. This was seminal work by Gerd Zuck in '88. He presented a finite element approximation and together with error estimates for the case omega equals 1. For the case effectively, formally omega equals 0, so as we see we can't actually take in this formulation omega equal to 0, but formally if we were to do that, then we just get back to the model which is derived by Barrett, Garker and Nuremberg, where they presented finite element approximations and stability bounds, but they didn't actually show convergence of their scheme. So the nice thing about this formulation, so this is all in R2, nice thing about this formulation from the point of analysis is that it's strictly parabolic problem, and it was easy for Elliott and Fritz to show an error analysis of this finite element approximation of this to the continuous solution. From the point of view of just approximations but no analysis, then corresponding formulations from Zuck, Barrett and co-workers, and Elliott and Fritz all exist for surfaces in R3, and I'll just mention the recent work by Kovacs, Lee and Lubick, so 2018, so they've actually shown error estimates for surfaces in R3, which is something that's been missing for, as we see, 20 years or so. So it's very, very nice result. So
Vanessa,
Yes,
can you
sorry.
explain a little bit about this the Turk trick? What
It's I won't do it now because time is short. It is it's quite
you make exchange of variables.
yeah, exactly. You reparameterize in terms of the harmonic map heat flow, and then you split the method into normal component and tangential components, and then by the time you've rearranged things, then this comes out. But yeah.
So you have another PDE, the harmonic heating flow is another
Exactly.
PDE.
Yes.
You use
yes.
the solution of that to change the variable.
Yeah, exactly. You reparameterize your x in terms of the solution of the harmonic map heat flow. So we now have a weak formulation. If I just take the Laplacian of u equals 1 and the Robin boundary conditions integrate over omega t, use Green's identity, then I get the following weak multiplied by test function, of course, then I get the following weak formulation of my PDE plus Robin boundary conditions. That's the weak formulation of the PDE, and then I couple this to my weak formulation of the curve shortening flow. And so once you've got a weak formulation, then it's easy to extend this to a finite element approximation. Roughly speaking, all you do is you just add h's to all of the terms and turn them into finite element solutions. So that's exactly what we're going to see now. So first of all, I'll derive a finite element approximation of the free boundary problem on the previous slide, and then also what we were interested in doing was deriving a diffuse interface approximation of this free boundary problem, which enables morphology changes to naturally occur, and as morphology changes occur in tumour growth, then that was our incentive for deriving a diffuse interface model, do a finite element approximation of the diffuse interface model, and then just present some numerical results. So from the point of view of the finite element approximation of the free boundary problem, we'll just start off with, so we want to approximate this curve shortening flow. So we've got two different things we're interested in. We're going to approximate our parameter little x by this capital X, and that is going to give rise to our approximation gamma h at time n is going to be an approximation of gamma t, and it's going to be parameterized by this capital Xn, which lives in this finite element space. We're just taking piecewise affine finite elements, and so that is associated with the curve on the left-hand side, and then on the right-hand side is going to be our approximation, our finite element approximation of the domain omega t, and so it's just the triangulated interior of gamma h. And so we've got our xn, which defines the curve, and then we need our solution uh to live in the interior in this omega hn. So we define finite element, two sets of finite element spaces. So we've got our vh for xn, and then we're going to define an sh. So again, we're just taking piecewise affine finite elements on the triangles in the interior. And so that naturally gives rise to the following finite element approximation of the free boundary problem. And I'm not really going to say much about that except for, so we've got this moving boundary. Our interface moves with forced curve shortening flow, and so this equation here gives us the new position of the free boundary. So when we solve this for xn plus 1, so given an xn, which is the previous position of the boundary, then we solve this equation, get a solution xn plus 1, which tells us the new position of the boundary. So here our boundary is in blue, we've got the nodes on the boundary, they are moved via the solution of this PDE to give us, for example, this, and what we see is, because we're only, with the solution of this curve shortening flow, we're only moving the nodes on the boundary, so all the interior nodes are staying where they are, and so we're going to get a very unpleasant mesh coming about. So what we clearly need to do is also evolve the vertices of the interior mesh. And how do we do that? So we now use the second method introduced by Elliott and Fritz in 2016. And again, they're using the Turk trick in a different setting now. So explicitly what they're doing is using it to provide good mesh properties for problems with moving boundaries, which is clearly exactly what we've got here. So what happens is that, so again, you use the harmonic map heat flow. The solution of that, you use that to evolve. So you're solving a PDE to evolve the vertices of the nodes of the interior mesh. And the nice thing is that this is a structure preserving algorithm. So if you start off initially with triangles which have good shape regularization, then you're going to, by applying this trick, that's what you're going to end up with. So it's effectively a conformal mapping. So it gives rise to these very nice, nicely distributed meshes in the interior. So the two things coupled together. So we know that the Turk trick is making sure that the nodes on the boundary, when you evolve the boundary, the nodes on the boundary are going to be nicely distributed, and then we use the trick again in a different form, which enables us to have a nice distribution of the interior nodes. And because we're studying this coupled system, like if we look at, because of the coupled nature of the system, because we want to evolve the boundary with the solution, the forcing comes from the solution of the interior, so you have to have a good approximation of the solution in the interior, because otherwise if you have a bad approximation of the solution in the interior, that's going to affect the how you move the nodes on the boundary, which then will in turn lead to a worse approximation of the solution in the interior. So because of the coupled nature, you really do need to make sure that you have good mesh distributions and hence good approximations to your solutions. So now I just want to mention briefly a diffuse interface approximation of this free boundary that we're looking at again. So this is in RD. So Bjorn is going to talk much more about these sort of methods in the next talk, so I'll be quite quick. But what we're going to do is we're going to approximate gamma by an interfacial region. So we've got this curve in R2, gamma of t, which is evolving. We approximate it by an interfacial region, so it now has some thickness, which is going to be associated with this parameter epsilon, which is going to be very small. And from this application, we can think of gamma epsilon as approximating our thin rim of neutron-rich cells that we had in the first slide. So we put the whole thing in a bounded domain, capital D, and the geometry of the problem is now encoded in this phase field parameter. So we've got this phase field parameter phi, such that phi is equal to +1 in the interior of the tumour, it's equal to -1 in the exterior of the tumour, and in the interfacial region, in this gamma epsilon, it varies continuously or smoothly from phi equals +1 down to phi equals -1. And so phi tells us explicitly whether the geometry of the problem, quite simply, and the interfacial region is defined by the part of the domain where mod, well, in fact, we'll see it in the next slide. So if we take the gradient of phi, obviously outside or inside, we're going to get 0, and the only place where grad phi is going to vary is going to be in the interfacial region. So that's the we can define the interfacial region by either the region where mod grad phi is non-zero, or the region where mod phi is strictly less than 1. So standard approximation from the phase field or diffuse interface setting for this force mean curvature flow takes the form of an Allen-Kahn equation. What we're choosing to do here is you can use either a double obstacle potential or a double well potential to derive the Allen-Kahn equation. If you use a double well potential, then you end up with the Allen-Kahn equation. What we've chosen to do is use a double obstacle potential, which gives us this variational inequality instead of, so it's an Allen-Kahn variational inequality, not an equation. So it might seem that you might ask, why are we doing this? Why are we turning something which is an equation specifically into a variational inequality? The reason we do this is because it gives us explicitly, if you use the double well formulation, then you, instead of having explicitly phi is -1 and explicitly phi equals +1, you get and the interior and the exterior, you'd get phi is approximately -1, phi is approximately +1, and then it's not so apparent exactly where your diffuse interface gamma epsilon starts and finishes because of this approximation, whereas if you use the double obstacle potential, you explicitly get phi is -1, phi is +1, and you get this sharp formulation of where gamma epsilon starts and ends. And we'll see that that's useful when it comes to our coupling that we see on the next page. So here, from the point of view of the, so again we've got this v equals beta kappa plus u over alpha, so where do the terms appear? So this phi t is associated with the time derivative, so we can think of that as being associated with the velocity. And then on the right hand side we've got this u divided by alpha, so u divided by alpha, so because we've got a variation in quantity, instead of just multiplying by a standard test function, we actually multiply by the test function minus phi to give us this variational inequality formulation. And then we can see that our curvature term is now approximated by, so we've got this Laplacian, we've got effectively, if we didn't use Green's identity, we'd have the Laplacian of phi, and then we've also got this 1 over epsilon, the phi over epsilon term, which is, so those two terms together approximate the beta kappa term in the sharp interface formulation. So this is, as I said, standard approximation of force mean curvature flow with the, I just mentioned that the pi over 4 on the right hand side is chosen so that when you take epsilon to 0, so remember that epsilon was the width of the interfacial limit, as you take that to 0, then you recover your velocity law v equals kappa plus u over alpha. And for our initial data, then we just take the signed distance, we take our initial tumour, gamma 0, we take the signed distance function d of x, and we just set if d of x is greater than or equal to epsilon pi over 2, then we have +1. If it's less than or equal to minus pi epsilon over 2, we have -1, so the exterior and the interior, and then we have this sinusoidal profile across the interfacial region associated with the distance function. And as I've mentioned, we're taking +1 for the interior, -1 for the exterior. So this is what Bjorn, I think, is going to be talking about in much more depth. We now want to think about a diffuse interface approximation of our PDE, which solved the Laplacian of u equals 1 plus the Robin boundary conditions, which in the weak form is written above. And here we use the ideas, so Berger and co-workers and Bjorn, Arbels and Andrew Lamb both came up with diffuse interface approximations of such a problem. So what we see here, if we look at the difference between these two equations, well, we've got, so in the first equation, we're either integrating over the interior of the domain, gamma omega t, or we're integrating over the boundary, gamma of t. Those are the two integrals we've got on the top. The next line, everything's over this bounded domain d, which includes omega and gamma. So we can see we've got the standard grad u, grad eta in both cases, and we've got u times eta, delta, but what we've got in the second line are these new functions. So we've got this zeta of phi and we've got a delta of phi. And if we look at the corresponding integrals above, so what we would hope is that our zeta of phi is going to be equal to +1 in omega t, and it will be 0 outside of omega t, and then we've got obviously a sensible approximation of the integral grad u, grad eta over omega t, whereas our delta phi, then this we want to approximate the integral over gamma of t, so in our case our gamma of epsilon. So what we want is that delta phi is going to be equal to +1 in gamma epsilon and then 0 everywhere else. And because we use the Allen-Kahn variation inequality, we know that phi is explicitly +1 inside, -1 outside, so we can just take our zeta of phi to be, for example, 1 plus phi over 2, and our delta of phi, this scaling 2 upon pi, we take it to be 1 minus phi squared, so then these functions do indeed satisfy the criteria that we're hoping for. So this is standard diffuse interface approximation. So as we see here, the Allen-Kahn equation is already in weak form, or the Alencon variation inequality. We've written our PDE in its diffuse interface weak form, so the finite element approximation is trivial. Here it is in general, everything now just has an H associated with it to tell us that it's a finite element function. Again, we're taking piecewise affine finite element functions. And what I would like to mention is, from the point of view of solving this on a computer, so we've got this finite element approximation, you have to be careful. So we're approximating this motion by mean curvature using the Alencon equation, and what you have to do is you have to make sure that you suitably refine your mesh in the interfacial region. So that's we have three different meshes when we solve this problem. So we have a very fine mesh in the interfacial region. So typically you need to have, so whatever value of epsilon you take, you need to pretty much have pi times epsilon is equal to, divided by 8 is your value of h. So you need pretty much 8, because the width of the interfacial region is pi over epsilon, so you need pretty much 8 grid points across your interfacial region, so you really need that to be a very fine part of the grid. And whereas outside, in the exterior to the tumour, we don't want to solve anything, nothing's happening whatsoever, so we can take as coarse a grid as we want outside, and on the interior then we know we need to solve this elliptic equation with the Robert boundary conditions, so we need to have a reasonably fine mesh, but not that fine. So we need to take care of, so we've got this adaptive mesh refinement going on, so all these things are evolving. And from the point of view of our problem, it's very easy for our refinement. We can just say quite simply that we want to refine a lot in the region where mod phi is less than 1, because we know that's the interfacial region. We want to refine quite a lot where phi is equal to 1, and then we just coarsen where phi is minus 1. And I just want to mention, from the point of view of analysis, so if I were to add time regularization to the elliptic PDE in my coupling, then we were able to show existence and uniqueness results to this diffuse interface coupled system, and we were also able to show the convergence of our finite element approximation in 2 space dimensions to the regularized the solution of this regularized model. So I'm just going to end with some numerical simulations. So whenever you solve anything using finite elements, provided you've not got too many bugs in your code, you should at least see a solution that looks quite reasonable. But what you don't know is actually whether what you're seeing is a good approximation of the problem that you're trying to solve, or whether there are still additional bugs in your code and you're not actually approximating what you originally thought you were. So it's always a good idea, if you can, to compare your finite element solutions or your numerical solutions with an analytic solution. So if we take the simple case, so this is still in R2, so we just take the case of a curve, our boundary gamma is just going to be a circle, which is either growing or shrinking, and we keep this radially symmetric solution, then we can solve Laplacian of U with the Robin boundary conditions. We have an analytical solution for that, so we've got an analytical solution for the boundary, analytical solution for U, and we just check that our solutions to the finite element approximation of the free boundary problem and the finite element approximation of the diffuse interface model do actually are suitably close to the solutions of the analytical solution. So that's what we're seeing here. So in the top row, what we have, so we have using different parameters. So we have 3 parameters, alpha, beta, and q. So here we're just taking q to be equal to 1.5 and the initial radius of our circle to be 1.5. And if you take those 2 parameters with alpha equals 1 and beta equals 0.1, what's going to happen is your circle is just going to grow. And so we see the radius plotted against time in the left-hand plot, and we've got the analytic solution is the blue dots, and lying on top of that pretty much is the solution to the free boundary problem, and that's in black, and then in red is the solution, in red is the solution to the free boundary problem, in black is the solution to the diffuse interface problem, and we can see that they're lying on top of each other very nicely, so we're optimistic that our numerical approximations are indeed correct. if we change the parameters, so if we see from in the left-hand side, we've taken epsilon to be 0.04. So epsilon, remember, is the width of the interfacial region in the diffuse approximation, and also remember that we need to take 8 times h to be pi epsilon. So the value of epsilon is determines the mesh size that you use. So the larger value of epsilon, the larger value of h you can use. And for the parameter setting alpha equals 1 and beta equals 0.1, to get the solutions lining up, it was sufficient to take epsilon to be 0.04, whereas when we changed the parameters, we changed alpha in particular from 1 down to 0.1, then to get this correspondence between the diffuse interface solution and the analytical solution, we needed to take epsilon equal to 0.01, so this meant a finer mesh size needed to be used to capture the curvature and hence get a good approximation. So at the top, it's just showing the radiuses, and then the final time, I think 0.4 or something, we're just showing a plot of the solution U along the from the center of the circle out to the boundary of the tumour, and we can see that again the three things line up. So now we're happy that we believe that our computational results are close to what we actually are trying to solve. Then we can look at more complicated structures. So we forget about the radial symmetry of the problem. We start off with a simple elliptic structure, and we see this evolution into this unstable. We see the competing volumetric sink and surface source bringing about these fingering instabilities that you see in many of the other tumour models. So here, the top row is the sharp interface, the free boundary problem results. The middle row is the diffuse interface, and then we're just looking at the geometry of the two. So blue and red is the phase field parameter. Phi is equal to -1 is blue, phi is equal to +1 is red. On top, there's also a white line, which is a plot of our curve, capital X, our numerical approximation to the parameterization, little x, and we see, so this is just showing the sharp interface lying on top of the diffuse interface geometry. So that's with one parameter regime. We now look at a different parameter regime. So in fact, we keep Q and beta fixed, and but again, so here we've taken epsilon equals 0.4 because 0.04 because we know that gave rise to good agreements with the model, and so now we've changed the parameters. So again, we've reduced alpha down to 0.1. So we're taking a smaller value of epsilon to make sure that we are capturing the correct geometry. And so we see less of a fingering. There's still see the instability, but the fingering is becoming less as we reduce alpha. And then if we take a slightly more exciting set of initial data, then we see the morphology gets more complex. And then the power of the diffuse interface model, as I mentioned, the reason we were introducing it was because it enables topology changes to be handled automatically. So here we see two initial circular tumours that just evolve in time and then meet and then form the fingering patterns that we saw previously. And then I'll just end with we can do all these things in R3, so instead of having an evolving curve, we now have an evolving surface, and in this particular case, we didn't use the methods of Elliott and Fritz in either case. We just used the method from Gerd 91 for the evolution of the boundary, and we used a harmonic mesh smoothing in the interior instead of the method introduced by Fritz and Elliott. And with that, I'll finish. Thank you.
Questions?
So you mentioned that when you were evolving these two-dimensional domains, so you were evolving the mesh points, and you said that happened in a structure-preserving way, in the sense that it was conformal or preserving angles. So now in the 3D setting, you have done something different. So is that comparable? Do you also have some structure preservation there?
No, so definitely, if you compare, so back to the 2D session, simulations, if you compare the solution that you get by using just the, wherever it is, using just harmonic mesh smoothing to the conformal mapping that you get from using the harmonic map heat flow and then Elliott-Fritz, then if you, for example, move the boundary up and bring it down again, and certainly for specific formulations, the standard harmonic mesh smoothing does not give rise to nearly, it doesn't. Yeah, so there is a significant difference. But the trouble is trying to, in two space dimensions, what you need to do for this harmonic map heat flow trick is you have this reference manifold, which is going to be, for the case of if you've got just a boundary in R2, your reference manifold needs to be a hemisphere in R3, and so from the point of view of a 3D computation, your reference manifold needs to be something in R4, and then that's not doesn't blend to coding very easily. So it's okay to do it for 2D because your reference manifold is going to be a hemisphere in R3, but yeah, as soon as you extend it, it becomes a bit tricky.
So I love this model and the things you did. There was this W parameter, this omega parameter for balancing the two different directions of the velocity. Is there? So have you seen some interesting things about that optimality, or?
That's a very. I haven't seen. I mean, certainly it seems that if this, to some extent, the smaller the value of omega you take, the better it is. Not taking it to be like I think if we took it to be 0.2, seemed to be quite a good value.
So 0.2 means little normal and much tinier.
Exactly.
Okay.
Yes. Yeah. It's certainly. But it would be interesting to know what sort of geometries give rise to what values of omega you should. It definitely makes quite a considerable difference. But
And then let's thank